now we are able to take the exciting step of actually doing some predictions. Okay, so first of all, let's define our goal, okay? Our scope is essentially, okay? We're not gonna look at all possible motions because that's way too vast a topic. We'll first focus on motions in one dimension, and the next chapter we'll look at motion in two dimensions. Okay, so that means every time it'll either be left or right, or going up or down. Okay, these are the two main things we'll look at. So every now and then, occasionally, be careful, is sometimes I could have an object rolling down a slope like this. All right, so in this case, it's not really left or right or up and down. It's right and down at the same time. So maybe you want to tilt your positive x-axis this way. It's still motion in one dimension because the ball is not going to jump out of the slope, right? It's just going to move along the slope like this if it's a simple situation, which we will focus on. So don't worry too much about complicated things. Everything is going to stick in one dimension first in this chapter, okay? And this brings me to a point is remember to define your axis or your system. Very important, right? This is probably the third time I bring this up in the class, in the course so far, because it is so important. And I've explained it in previous videos. When most of the time, positive x just refers to the right and positive y refers to the top. However, I'll give you two scenarios. There's a good chance, I would say maybe like maybe 60% of the time that's true, but up to 40% of the time, it might actually be worthwhile and be wise if you do it the other way around. For example, if I have a car that is moving this way and it's accelerating this way, so it's going to get faster this way, right? So it's going to increase its speed this way. Everything's moving this way. It will be almost dumb to make all the numbers negative, right? Negative something, negative. So you have negative on negative, which is you're making your own life more difficult than it has to be. So let's just make positive x-axis this way, right? So this is an example where making left-hand side the positive x-axis it's worthwhile. So remember, in your exam, make sure you have a small legend somewhere in the corner in your solution, maybe on the right. That's fine as long as you have somewhere telling me which way is positive x. Just draw a small arrow like that. If it's 2D, right? Draw something like this. That's fine. If you need to make x this way, then so be it, right? Another example where we use the non-standard xy direction is, for example, if I have an apple, right? A falling apple, right? The famous one that falls on Newton's head. So it goes down, right? So this is exactly the same way. It's going to accelerate downwards. The velocity is going to go down. It's almost making you're making your own life miserable if you define y to be that way. Might as well make everything go this way. Okay, so make that the positive y direction. Now, both ways will work, and a lot of times it will give you the same answer or a correct answer, at least, as long as you define that correctly. And I'll show you in the following examples, we'll see sometimes both will work. But in either case, right, either one works. You just need to define it. Make sure you do that. Okay. There's one more criteria. This is the most important one. We're gonna specialize in one type of motion first, one at a time. And this is called constant acceleration motion, or constant acceleration problems. Yeah, let's call that. Okay, constant acceleration problems. I like the word motion better. It generalizes to what we're gonna do next. All right, either way, problems that focus on constant acceleration. What that means is A is a constant, right? And that means the average velocity is the same as instantaneous velocity. Okay, we don't have to differentiate that. So as we remember, right? So the acceleration is going to be constant, but be careful. The velocity is not necessarily constant, because if you're constantly accelerating, the velocity gets faster and faster. The position or the displacement, of course, is not constant, because you will be moving away from your starting point, your initial position, right? You have displacement. So all these are not constant. The time is going to take, but we're going to focus on this fact. It makes this a little bit easier. Okay. Now, comments. At first, you might think that this is very limited, right? Because if I stomp on the gas, if I'm driving, it might not be constant acceleration, right? It could be fast or slow. At first, looking at this, you might think, hey, this is a pretty limited scope, pretty limited goal of ourselves. We're looking at one dimension and also just constant. But believe it or not, a lot of a wide class, almost half of the time, most of the motion is in one dimension, and it's at constant velocity. To give you an example, right, a falling object in free fall, the only force you've learned is gravity, and it means everything accelerate with the same value. It's the acceleration due to gravity on Earth, right? Remember, that's A equals to G 9.8 or 9.81 downwards towards the center of the Earth. So everything that falls, in fact, if I throw this up and down, the whole process is in constant acceleration downwards. We talked about deceleration. So on the path upwards, you can see the motion gets slower and slower until it's sort of, the speed stops momentarily, instantaneously there, and then it speeds up again. So it slows down, that's deceleration, and then it's acceleration. We'll try not to use the word deceleration, right? So it's always constantly accelerating downwards, right? So it's only the first leg it's slowing it down, and second leg it's speeding it up. So anything that moves under gravity is a constant acceleration. And if you roll a bowling ball, for example, if you play bowling and roll a ball across the lane, it actually slows down at a pretty constant rate most of the time. Friction works that way. And a lot of times it is, so it actually takes care of a wide class of problems. Most things are in one dimension. As I said, around, let's not say most, around half of the thing, the other half is in two dimension. Very rarely things actually genuinely move in 3 dimension, because let's say I throw this pen like this. Yes, it's in 3D space, but if you really think about it, it is on this plane, right? It moves 2D, but it doesn't halfway sort of turn around. So very few things actually utilize all 3 dimensions during its path of motion. So that's one reason we'll not really need to talk about 3D. And the second reason is when we go from 1 dimension to 2 dimension, there's new skills involved. But when you go from 2 dimension to 3 dimension or higher dimension, I don't know what that means. I don't live in 4 dimensions. If you do, you can you can imagine that. But the skills are the same when you go to higher dimension. It's only going from 1 to 2. You need to know how to take care of more than 1 dimension, and then it's the same skills. So number one, most things don't actually genuinely move in 3 dimensions, so we don't worry about it. Number 2, the skills are transferable after that. All right, so we'll first deal with 1-dimensional constant acceleration motion, and then the second. One more motivation is, remember, acceleration is to do with force, right? Is to do with the net force. So if there's multiple forces on the object, right, you draw a free body diagram. If there's lots of forces, just calculate the net force, that will give you the acceleration. And we are going to focus on forces are constant force on it. So we don't have time varying or changing force. It's going to be a constant force. So constant acceleration motion is closely related to constant net force on an object. Okay. What's really difficult if you have different, if the force is changing all the time, right? However, don't worry. Throughout the whole course, you will almost you rarely need to talk about that. There's some simple exceptions, but we'll get to that. We'll focus on the simple files first, and we'll build on it. Okay. Now there are 2 approaches to doing these type of problems. One is the easy approach, and the other is the harder one. A better way of saying it is, no, that's the best way to say it. So there is sort of the better way to say it is, there's a sort of shortcut way, and then there's the formal way. Okay, and the shortcut way is what I call, or what's standard called the Suvat equations, or Suvat approach. Okay. Okay, and the other one, I'll just call it the formal approach. Okay, so the Suvat approach is basically, you are able to do this without calculus. So this is a non-calculus approach, and this one is well prepared for you to do calculus type problems as well. So you can do non-calculus type problems or calculus. So this is more general, and it extends easier in the future as well. So for the 1% of the time you need to deal with changing accelerations, then that would be easier. Okay, just to give you an example, right? It's called a Suvad approach because it involves using equations with the variables S, U, V, A, T. You can probably recognize some of them already. Remember what does S stand for? What does U stands for? What does V stands for? What does A stand for? What does T stand for? Right, we'll get to that. But it involves equation like that. So for example, one equation looks like this, right? V equals U plus AT. We'll see that in the future, right? So this is one of the Suvat equations. But in the formal approach, it looks like this. Okay, which one do you prefer using or remembering? So this is very much easier, and we'll talk about both at the same time, or one after another. But I'll start with what I call the easy way. And there are, of course, pros and cons for both. And I've stated one over here. And another one is this. So is more generalizable to any acceleration, this approach. And this one only works for constant acceleration motions or problems. Okay, so this is important. If A is not constant, this easy approach just falls apart. All right, so you cannot generalize it at all. Right, so there's one use for this. And secondly, this is actually easier with multiple objects. And this is harder for multiple objects. So if I drop two pens, one after another, so if I drop this one first and then this one 1 second later, and I want to see at the point of strike, how long what's the difference? So if I separate them by 1 second over here, what's the separation in time when they land? Do they land also 1 second later, or does that actually increase, right? It's a good problem. You can think about it in a moment. It's a little bit harder with the Suvat approach. It's good with one object, but if you're really clever about it, so 80% of the time we're going to deal with motion with just one object, but there's around 10 to 20% of the time you might have two objects. So if you're really clever about it, you can also use the Suvat approach, but that's also a reason why we also want to learn that, because it is slightly easier with the formal approach as well. All right, so having said that, we'll jump right into Suvad approach, and you'll see how easy it is to analyze this type of motion in one dimension and constant acceleration.